Section 6.2, separating and differentiating. Separable differentiable equations. Now, these normally come in the form of dy over dx is equal to some function over here. Normally we see it in terms of x. Now though, we're actually going to look at it and see that sometimes it'll even be in terms of y. X and y possibly. For example, we could have x squared over y plus 1. To solve this, although it looks big and scary, all we have to do is separate the two and integrate. So what we're going to do is we're going to get all our y's on this side and all our x's on this side. So first thing I'm going to do is multiply both sides by dx. I'm going to get dy is equal to x squared over y plus 1 dx. And we'll get the y's over here. So we'll multiply both sides by y plus 1. So those cancel. And we'll get y plus 1 dy is equal to x squared dx. Now that I have that, it's a very simple matter. If I'm trying to solve this for y or solve it for x or some variable, I can just antiderive both sides, just like that. And this is going to give me, of course, y squared plus y plus some constant. Now the constant on the left side might be different from the constant on the right side, so I'm going to put c1 over here. And antiderivative of x squared is 1/3 x cubed plus some other constant over here. And I could solve this for whichever one I want to, really. But what I'm actually going to do here is I'm just going to go ahead and get this over here and bring this constant over here. So if I subtract a constant from this side, just like this, I'm going to get y squared plus y is equal to 1/3 x cubed. A constant minus a different constant is still just some constant. You can put constant sub 3 or k or whatever. And I'm going to go ahead and pull this over here. Y squared plus y minus 1/3 x cubed is equal to some constant. Now we've actually seen this before. This is what we'd call, we used to have to do this with implicit differentiation. So these are just going backwards from implicit differentiation. This is one method for going backwards from implicit differentiation. If I had wanted to, I could have stayed right here and completed the square. Y squared plus y. Now the constant here is 1, so if I divide that by 2, I get 1/2 squared. I'm going to add 1/4 to this side. Is equal to 1/3 x cubed plus c plus 1/4. Now that of course is just going to give us some other constant. This would give us y plus 1/2 quantity squared is equal to 1/3 x cubed. I can leave the c in there, or I can combine these, just say a different constant. Let's call it k. So y is equal to plus or minus the square root of 1/3 x cubed plus some constant. Oh, sorry about that. Y plus 1/2. Then I'm going to add 1/2 to both sides. Slide the paper up. Y is equal to plus or minus the square root of 1/3 x cubed plus k minus 1/2. So that's a way I could solve for y if I needed to. So all you have to do is get the x's on one side, the y's on another, and then we end up solving from there. This is normally seen in the following. The rate of change in the growth of a population is directly proportional to its population. We can write that like as the following. The change in population over the change in time is equal to some constant times the population. If we think about this, the more people there are, the more people are having kids, so the faster the population is going to be growing. If there's fewer people, times whatever constant that is, we're going to have a slower population growth. So let's go ahead and solve this then. Got to get all my p's on one side and all my t's on the other. Well, there's no t over here, so I'd really just have to move the p over. So I'm going to multiply both sides times 1 over p. So I'm going to get 1 over p dp over dt is equal to k, and I'm going to multiply both sides by the dt, and that's going to give me 1 over p dp is equal to k dt. So I have 1 over the population times the change in population is equal to the constant times the change in time. Now we're just going to antiderive both sides. The antiderivative of 1 over p, well, that ends up being the natural log of p. And that's going to be equal to, and this would be plus some constant. I'm not going to put it here, though, because I'm going to put it on the other side. Doesn't matter what this constant is. Maybe it's 5. Antiderivative of 5 would be 5t. But this is k times t. And I'm going to put plus some constant over here. Now what I'm going to do here, I need to solve for p. Well, how do I do that? Well, I'm going to exponentiate both sides. So p is equal to e to the kt plus c. Now, if we remember our properties of exponents, this is really, I can rewrite this as the following. E to the kt times e to the c. Just like if I had 2 to the 4th times 2 squared, it would give me 2 to the 6th, which is 4 plus 2. 4 plus 2. This is kt plus c, which is kt times e to the c. Now, e to some constant, e raised to some constant is really just some other constant. So let's put that, call that, how about k? That's a good one. Let's not use k because we already used that up here. I'm going to put p sub 0, and I'll tell you why in a few moments here. So what we have here is the population at any given time is e to the kt times p sub 0. Well, you may recognize this slightly differently. The starting population times e to the kt. What if we replace that k with an r? It would be the starting population e raised to the rt, or our good friend PERT. So the population at any given time is the starting population times e raised to some rate of growth times time. So this is where PERT comes from. When the rate of change in the growth of population is directly proportional to its population, we get this differential equation right here, which leads us to, through some calculus, PERT. And we know that all the applications of this, like if you invest some money and it's compounded continuously at an interest rate of, let's say 5%, you could find out how much that would be in a certain number of years. You could say, hey, the starting population of Greencastle is like 9,880 in 1990. It grows by 6% a year. You give me a time and I can estimate the population of Greencastle. This also works for exponential decay. With a car's value is $18,000, but decays at a constant rate of, let's say, 15% per year. I can figure out how many years until it's only worth, say, $7,000. But all that comes from this right here. So most of the equations that we're going to deal with, it's going to be something like this. They may have you set it up, and you'll have to anti-derive and solve. Now that you recognize this one, do you have to go through it over and over again? No, not at all. But they may say it's directly proportional to the change in population over the change of time is directly proportional to the change in population plus 50, or the population plus 50. Or it may say the square of the population, which would be p squared. They may say the square root of the population. All sorts of different ways that you can calculate, that you can do these separable differential equations. I'm going to do one more example for you here. I just made up this problem off the top of my head. Let's hope that it works out for us. But the change in y over the change in x is equal to y squared times e to the 2x. So we're going to have to solve this and find the particular solution when y of 0 is equal to 5. So first, let's separate this thing. I'm going to get the y's on one side, so that means it's going to be 1 over y squared dy is equal to e to the 2x dx. Now I'm going to integrate both sides here. Remember, this is the same thing as y to the negative 2, so I'm just going to use the power rule on this. So this is going to become negative y to the negative 1, and there could be a plus c here, plus some constant, and the antiderivative of this is going to be 1/2 e to the 2x plus some constant. Now you may be saying to yourself, how did Mr. Kuhne figure that out? Well, I actually thought of it. Why didn't I use substitution on this? I figured I didn't really need to, actually. If I derive e to the 2x, I know it's going to be e to the 2x times 2 by the chain rule. But this doesn't have a times 2 in front, so I pulled a 1/2 out front there. This is some other constant. So if I combine the constants here, I'm going to rewrite this, negative 1 over y is equal to 1/2 e to the 2x plus some constant. Now that we have our general equation, we need to plug in our point to find the particular solution. So when y is 0, it means x is 0 there. For y of 0 equals 5, 1/2 of e to the 2 times 0 plus c is equal to negative 1 over 5. And so this is going to give me negative 1/5 is equal to, that's just going to become 1/2 plus some constant, or c is equal to negative 1/5 minus 1/2. Common denominators is going to be negative 2/10. negative 5/10, so we're going to get negative 7/10 is equal to C. And come back up here, and we're going to plug that in here. And I'm going to get negative 1 over y is equal to 1/2 e to the 2x minus 7/10. Just to be clear, that is not an exponent. Now, generally, we want to solve for y, so I'm going to take the opposite of this. And I'm going to then take the reciprocal. So y is equal to 1 over, I'm just going to switch these two around, 7/10 minus 1/2 e to the 2x. Now, this is a fairly typical problem, fairly standard problem that you'd see on the AP exam. Just so we're clear as how the breakdown would normally work, it would normally go like this. 1 point for separation of variables. So just by separating it right here, the y's and the x's, you would get 1 point. You get 2 points for anti-deriving. And from here, you only get the next points if you remember the constant of integration. So 1 point for constant of integration. You would get 1 point for using the initial point. And 1 point for solving for y. So 1 point for getting your final answer there. So this whole thing on an AP exam would be worth 6 points. Total of 6 points. Now you only get, they would normally say, note, maximum 3 out of 6 if a student did not consider the constant of integration. So if you forget the plus c right here, the most you could get is 3 points. That's the most you can possibly get. So that plus c is so extremely important because it allows you to do the others. Let's say you use the initial point. Let's say you make an error in here and you get that as negative 3/5 instead. You wouldn't get that point, but you'd still get these two for using the initial point and remembering the constant of integration. So that plus c, once again, is so extremely important. Don't forget the plus c. Thanks for watching.